first day of review session, and this is both in person and online. So I will attempt to post this entire thing to YouTube, hopefully by watching the video. If you are watching the video now, it has succeeded. All right, so this is review for the final exam. And so I'm going to tell you parameters for the final exam. First step of the law is 12 questions. They are short answer, graded with partial credit. As all the previous exams have been. So essentially the same format, just a little longer. It is cumulative. So it covers all the material in the course. With the most recent material, we're talking about integrals in exactly the same proportion that it falls in the course. So integral related problems. You should figure there's about 3 of them or so. I haven't actually written them down yet, so there may be 3, there may be 4, there may be 3 in a few parts, so about 3. But it is otherwise cool. Okay, what are you allowed to bring? Well, you're allowed to bring a formula sheet as before. However, this being cumulative, I'm going to have you bring 2 handwritten 8 1/2 by 11-inch sheets, all sides. As before, no electronic calculators. If you bring mechanical calculators, that's okay. So if you have an abacus or a slide rule, we saw slide rules earlier in the course. If you want to bring a slide rule, awesome. I don't think it will help you, but it's a good luck charm. If you bring a quantum computer or want to be on your research group, you will be recruited on spots. They now actually don't even exist. That's an interesting article about them this week. But in any event, right, let's see here. So I guess that's the exam. Yeah, how long is the thing? Right, it is Thursday, 12th of December, and it is from 8:55 a.m. to 11:55 a.m. And of course, with final exams, the question is often where. The answer is here. Okay, I guess that's basically the mechanics. What questions do you have about formatting of the exam? Anything like that? Any questions at all? Yeah?
Just going to be like the other exams?
It's going to be formatted exactly like the other exams. Yep. So same level of difficulty, same type of questions. It's basically just making sure that everything that we examined before stuck. And there's a little bit of integration of some of these concepts, sort of across the course material. Yes?
Is it more concepts or numbers? So like, will we have to know like real-world applications again?
I'm not focusing very heavily on real-world applications.
Okay, so it's mostly just going to be numbers.
It's mostly computational. Yeah, I'm not going to say on some of the previous exams I've asked you, give me some examples of this or show, not so interested in that at this point. As far as I'm concerned with those learning objectives as called out in the syllabus, those have been addressed. Other questions? Okay. Well, let me see, a bunch of you showed up, so let me pass out a few more homeworks. And I want to keep this format loose and reasonably flexible. But usually what's good is for me to set the stage by showing you a bunch of, sort of reminding you a bunch of things that we've done, going through the syllabus, talking about each of these learning objectives, because I take those very seriously. When I say, after this unit you should be able to, that's going to be something I'm going to be testing. Yeah?
I know I brought it a little bit late, but did you go over your office hours?
Ah, that's an excellent point. Let me give those logistical pieces of information next. That is an excellent question.
Thank you.
You're welcome. Okay. Great. All right. Right. So office hours. Good point. In fact, actually, let me. Why don't I do this? To be completely unambiguous, I will list all of the office hours for the rest of the semester from here on out. So, office hours. So, first of all, today, 1 to 2 p.m. Sort of that usual office hours slot, still good. Tomorrow, 9:30 a.m. till beginning of this class. That's still good. Tomorrow, normally I have a 1 to 2 p.m. slot. That's not going to be held. But I do have a 6 to 6:30 p.m. And then next week, next Tuesday, and next Wednesday, both days from 10 a.m. to 2 p.m. So that's 4 hours through the middle of that finals week where I'm around. Explicitly, door is open, you don't need an appointment. If these times do not work for you, let me know. I will make time for you. So, or email, or appointment. I'm actually often around doing various other things, so if I happen to know these times don't work, I can adjust things to make sure that I'm there for you. Okay? All right. Good?
Thank you.
All right. What other sorts of things do you want to hear about logistically before we go into content? Good? All right.
What part of our grade is this?
What part? That question would be answered by the syllabus.
30%.
What's that?
30%.
I think that sounds about right. Yep, 30%. 30%. So yeah, actually, let's. If you look on the syllabus, the last page of it says 10% is your homework. Let's sort of do this sort of reminders. I'm grading. Right. So 10% is homework. 20% on exams 1, 20% on exam 2, and 20% on exam 3. And the balance, 30%, is on fun. So what remains is that. So it's basically like one of the exams, but it's a little more weighty because it is paper. Okay. All right. And right, I also have along the syllabus, I tell you, you can see exactly where you stand right now by tabulating out and weighting your scores. So if you go through the homeworks and compute your homework average and put in those weights, you can see exactly where you stand. All right. Anything else? All right. Now let's do content. Okay. So the guide for understanding the course content and the guide for understanding what that I'm going to be examining in the final exam comes entirely from the syllabus. The syllabus is your go-to, and you can tell what is important to me and what is not by reading the learning objectives. So it says, for instance, the first unit says limits and derivatives, so state and explain definitions for the concepts of limits, continuity, derivative, as this pertains to functions. Use these definitions to actually compute things. Explain why they're important for understanding certain behaviors of functions. And then it also says here, give an example explaining the importance outside of mathematics, and as was just asked, be addressing that on the previous exam. So I'm not so concerned about that one. If we look on Unit 2, well, I want you to compute derivatives of things. And I tell you what kinds of things: polynomials, exponentials, logs, trig, all of those sorts of things. State properties that are useful. Use those properties. How are they useful for describing rates of change? Why are those properties helpful? That kind of thing. And then the third unit is applications of these derivatives. So once you know conceptually what they are, you can compute them. Now we're going to use them. And this is really the big focus on graphing. Sketch graphs of functions and understand maxima, minima, concavity, inflections, all that good stuff. Compute indeterminate limits. Use concavity to solve optimization problems. And by solve optimization problems, I mean those that are more or less confined to mathematical interest at this point. So find the maximum value of this function, as opposed to find the maximum volume of a particular object that's being used with sales. So again, not dealing with optimizing outside of mathematics. Okay, then last unit was integrals. And that should be hopefully still fresh in your mind. We've got definitions. So what is the integral as a limit? What is it as an area? So as the Riemann sum as an area, but also what is it in terms of an antiderivative? How the fundamental theorem knits these two ideas together. And use that to compute things. Use both of those definitions, both the Riemann sums, which are of course a bit of a pain, but entirely possible, and also use the fundamental theorem of calculus to use antiderivatives to compute as well. And we have some computational tools in that regard. Okay, so those are the objectives. So what you should take as advice is, if those are the objectives, and I'm telling you them now, I've written them in the syllabus, which is essentially my contract with you about what the course is. It's a pretty good guide about what I'm going to be attempting to test. Now, how exactly the mechanics of doing that go out is by doing questions that hit on these specific items. So now this is where we delve into the book and address questions that are of similar sorts to questions we've done in the past, and some that may be a little different, trying to, as I said, sort of knit these ideas across the whole course. Not a whole lot of that, because it makes it a little hard to understand which objectives are being addressed, being systematic, but on the other hand, I do want the integration to happen. Okay, so I think probably the most sensible thing to do is start at the very beginning of the course and sort of sweep through. That way we can put most of the emphasis on things that are sort of the oldest and you may have forgotten. And the things that are newer will get sort of pushed to the end, and you will have seen them more recently. We have 2 days of review. This is the first. And so by the end of tomorrow, we should have covered the whole course. Now, I want to keep the format open. I don't have a particular set agenda. I don't have a particular set of questions I want to go through, or even particular topics I want to talk about. If you say, open the book and show me a certain question, I will happily do it. So I think the way you can get the best use of your time is by having done some problems, perhaps even going back into the old homework problem sets and say, gosh, do I remember how to do this? And if the answer is no, ask. So I'm going to start off by asking, has anyone done this yet? No. No. Yeah, that's good. That's fine. That's more or less what I'm expecting. Hopefully by tomorrow, a few of you will have done this. But I'm happy to start seeding some ideas. Yeah, go ahead.
I know it's not at the very beginning of
That's
the course,
fine.
but can we do an optimization?
We can do an optimization problem. Sure. Let's see here. Do you have a particular type of optimization problem that you really want to see?
Something with volume.
Something with volume. Sure. Something with volume. Well, okay, so it's not sort of applied math, so to speak, but volume is, that's as old as the hills, and people don't have to worry about whether or not that's applied or not anymore. Pure mathematicians can safely do volume without losing their pure status, which is of concern to some of them. Okay, so let's see here. Maybe something like this. Volume. So this occurs in section 4.7. So, maximization. That's a maximize or minimize. Minimize a function. It's not a problem. And those are typically found in section 4.7 in your book. And so there are quite a few of these here. And you want one with a volume.
Or just one in general.
Or just one in general. Okay, all right. There are some that involve sums of numbers and distances and that kind of thing. Oh, here's one that's cute. If it's just a general one, let's take a look at this one. Let's look at 4.7, number 5. It asks, what is the maximum vertical distance between the line y is equal to x plus 2 and parabola y is x squared, for x values being between -1 and 2. Okay, so that's the question. The question is, what is the maximum vertical distance between these two geometric figures? Is this the sort of question you will have in mind? Okay, so once you've got this statement there, it's a matter of trying to decode what it is that we're asking, what function needs to be optimized. What function needs to be optimized? What function needs to be optimized? Well, it's the vertical distance between these two curves. Okay, well, perhaps what we should do is we should plot these two curves so we have some understanding of what we're looking for. It's not strictly necessary to nail down the problem, but it really helps in understanding what it is that you're after. Okay, so the line, what's the slope of this line? 1, right, and its y-intercept is 2. So here it is, and it's a slope 1, 1. Okay, and parabola x, y equals x squared. Well, it's going to start up and go sort of like this. Of course, what might happen is they might intersect, or they might not. So let's check. See, the line starts out above the parabola. So what's their two values at -1? What's the value of this function at what's the value of this function at x equals -1? 1. And what's the value of this function at x equals -1? 1. This is -1. And on the other side here, what's the value at x equals 2 for this function? And what about this one?
4.
There's, okay. So vertical distance there is 4. So if they had asked the minimum vertical distance, this would be a wicked easy problem. Because you'd be done after graphing. You say, oh, minimum vertical distance is pretty clearly 0. Curves intersect. But they're asking not for the minimum, but for the maximum. So let's try to write a function that describes that vertical distance. That's this distance here. So this is what we're after. We'd like that function. Okay, well, let's label these items. That's convenient. Y is equal to x plus 2. That's this guy, and this guy is y is equal to x squared. Okay, so what is this function f? Well, what you can do is you say for a particular x value, say here, it's the value on this line minus the value on this parabola. That's what this distance would be. And I don't need to worry about absolute values or which one's bigger or smaller, because on this interval between -1 and 2, the line is always giving you bigger values. Okay. So the function to be optimized, we can now answer that question. That's f of x, and it is the line of x minus the parabola of x, which is x plus 2 minus x squared, which of course is this function, just erased the parentheses for amusement. Okay, so, well, let's see here. How do I find maxima or minima of functions? Well, if the function is differentiable, has a derivative, maxima and minima occur, well, basically one of two options. Either it's going to occur somewhere inside this interval at a situation where f prime, the derivative is 0, or since the endpoints are included in the interval, they might be at the endpoints. Now, does that happen at the endpoints in this case? No, because we already know those are minima. We already know those are 0, and the distance gets bigger. So, strictly speaking, maxima can occur where either at endpoints or at critical points where f prime of x is equal to 0. We already know this is already ruled out by the graph. That's already ruled out by the graph. So the only place where a maximum can occur is wherever the derivative of this thing is 0. So let's go hunt those points down. Sort of eyeball, you can guess where that maximum is. It's like it's maybe just a little over here, a little to the right of 0. Okay, so let's go ahead and compute f prime of x. Let's see, here's f of x. So if we take the derivative of x, that's what? 1. And what's the derivative of 2?
0.
Right, so don't bother writing that. Derivative of minus x squared is? Minus 2x. Yep. Okay, so I want this to be 0. So I want x for which f prime of x is equal to 0, which is 0 equals 1 minus 2x. So x is equal to, let's see here, I move the 1 over to the other side, and it's 1/2. So the maximum occurs at x equals 1/2. So right about here is the maximum. Now, strictly speaking, you ought to prove to yourself that this is a maximum. But how can we do that? How can we justify this as being the maximum? Well, there are various ways, yeah.
You can plug in 0.5 in each equation and then a couple of other numbers.
Other numbers nearby. That certainly gives you some evidence that you found the right answer. It doesn't prove it conclusively. I mean, your function may do something really awful right near here. It doesn't, but it could in principle. You're right. What else could it do? Yeah, you could take the second derivative. And what is the second derivative going to tell you? It's going to tell you about concavity. if your second derivative is negative,
Bless you.
negative, that tells you that your function came up to the spot and now is starting to go down again. And it's going down on the other side. So the second derivative test is a good way to check that. Okay, so that's conclusive. What else could you do? What else could you do? Look at the graph. Right. It's pretty clear that there's some maximum, and there's really only going to be one maximum, and that's it. So the graph is also a good way to do this in a nice and conclusive fashion. But we can do the second derivative test in one line. So let's see, the second derivative of this f function is the first derivative of this, which is what? -2. Oh yeah, that's less than 0. So what does that say? That says any critical points are local maxima. We've got only one critical point. So it's the local maximum. And that's really the end of the story. Does that help? Awesome. Other requests specifically for other types of problems that have given you pause in the past? Yeah.
Could we do a
Linearization, sure. A whole bunch of thank yous. All right, linearization is a sore point. Okay. Let me set the stage by reminding you what linearization is all about. Linearization is all about taking a function and trying to approximate it by a line. Now, the nice thing about this is that lines are really easy to use once you've got them. So they're really handy approximations. Most approximations that I've run across that are used in general practice come from linearizations. So if f is a differential function, at x equals a, then the linearization at a is, well, we've had various ways to compute this. Either you can sit down and do it ad hoc each time, compute a derivative, try to find the equation of a line through that point. That's perfectly fine. One thing we found midway through the course is that there's a nice simple formula that just does it for you. And what it is f of x is approximately the function f of a plus f prime evaluated a x minus a. So on this side, this is the actual function. And on this side is the equation of a line. So what linearization does is it says you can approximate this function here where? Nearby what point? Is it any good way off at x going to infinity? Probably not. Yeah. Is it any good when x is really, really far away from a? No, no way. It's only really good nearby a. And it really depends exactly on the nature of f, what all the other derivatives in this function, what they are. So this linearization, it's good. It's a good approximation. Here, x equals a. And it may be of dubious value farther away. Yes, I'm setting the stage. All right.
In such a rush.
All right.
I suddenly got really confused. Wait, when you're doing it, do
leave x as x, or do you plug in a value for x? That was my question.
Okay, so that's sort of your question.
Yeah, that's what I wanted to do.
That's why you want to do a problem. That's an excellent question that I agree. A problem helps clear that up. It's also helpful to understand that from a general point of view, too. So in this discussion here, let me grab my handy colored chalk here. I'm going to highlight the things that don't change. Highlight them in blue. I'm going to highlight the things that do change in red. So the function is under discussion. We're not changing that. The point where we're trying to get a good approximation, A, that doesn't change. That's fixed from the outset. What we are varying, though, is we are going to vary x. So when you look at your linearization of this function f, the function doesn't change. You're allowed to put in many different values of x on this side. Well, this is a function of x. This ought to also be a function of x. So really, all of this here does not change. This does not change. The only thing that is allowed to change is here. So this is a function of x, so is this. They're different functions. This one here is a line. This one is whatever it is. So now, it depends on the particular problem. If the problem just asks, give me the linearization, then you end up with this whole thing. If they say, use the linearization to approximate the value of a function, then you construct this function, and then as a second step, put in the value here. So you have to read the question carefully. Okay, so now let's look at the question. All right, what section is linearization? I think it's 3.10. Okay, I'll write that like this is section 3.10. Okay, so let's see here. Actually, why don't I do this? Here, pick one. We did not discuss the concept of differentials. But why don't you pick a linear approximation problem? That looks good. Where are the tough ones? I don't know. They're in there somewhere, I guess. What's that? Higher numbers? Higher numbers.
Can we do 44?
44. All right, the last problem in the section. Sure, except for the fact that doing the arithmetic may be a little tricky. But that's fine. All right, let's look at number 44. It's a good problem. It's a good problem. You have a calculator. All right. Now you've got a calculator. I know what to do otherwise. So this is okay. So let's have a look at this. The last linearization problem in the book. At least the last one in that section. Okay, so it says suppose we don't have a formula for g of x. But we want to know something about g of x. But we know the following. First of all, we know the value of this function at a particular point. We know the value of g of 2 is -4. And we also know what the derivative is. We also know that the derivative, g prime of x, is square root of x squared plus 5. Now, the question is, estimate g of 1.95. They also ask you to estimate g of 2.05, but this will be enough to get the point of this. Now, we know what g prime is. We know what the value of g at 2 is. Now, thinking about this from a, now that we've finished the course point of view, or at least we've finished the course material, freely admit the course is not over till the final is. Well, actually, can we figure out what g is? What is g? What's a way to write down what g is, even though we don't have a formula for it right now? We can obtain a formula. Yes, we can take the antiderivative. Now, part of the reason why we don't have a formula for it is because the antiderivative is kind of nasty. But let me put down as an aside. G of x is the antiderivative G prime of x plus some constant. Right, so it's going to be this. So we actually do have a formula for G of x. It's not an explicit formula for which all the functions have been resolved into things you can punch into your calculator. But there actually is a way to figure out what G of x is through the antiderivative. Right, so that's end aside. Let's use the linearization formula right here to compute what G is, or at least compute what G is near this value here, or estimate it. Okay, so here's what I'm going to do. So let's take our formula. Our formula says G of, we want to know G of 1.95. G of 1.95 is approximately what? Well, we need to evaluate G at a particular point. The only point they give us is at 2. So this 2 right here, this 2 is the A in our formula. So we're going to evaluate it at G of 2. Well, if we've chosen the A to be 2, that means if we're going to use this formula, we have to evaluate G prime at 2. And then what is x? 1.95. So that's what the linearization formula says we ought to do. Okay, so now let's put in a piece of information we've got. So what's G of 2? Negative 4, right. What's G prime? Well, it's that formula there. So let's put it in. G prime of 2 is put in the 2 for x there. So 2 squared is 5. So G prime is 1.95 minus 2. Yeah, in principle, at this point, all calculus is done. There's some numerical value, you can punch that into your calculator. So equals calculator. You can do that on your calculator. I don't think it's particularly enlightening to do at the moment. Okay. Yeah.
So like, I was thinking that we would have to prove if that was right. Like going to the equivalent, saying that 2 is like right 0 or a static and all that.
Nope. Nope. Linearizations are meant to be easy to use.
Okay.
They are this easy to use. Now, there is, though, the question, what I think you're hinting at is you're saying, you know, what do I should do something to know, you know, is this a good answer or not? Is this a good approximation, or is this approximation bogus? Because there's certainly the possibility it comes out that it makes no sense at all. And so let's try to answer the question, is this estimate and over or under estimate? How good of an answer is it? How would I figure this out? You have a calculator. Oh, okay. Yes? Yes?
It's negative 4.15.
What's that?
If you cannot do arithmetic on the exam, maybe we're going to use this calculator.
Well, if you cannot do it,
You're going to do it.
you are welcome to do it. provided you've got this part here.
Because if I do calculus and then attempt to add, that's.
No, if you do calculus, if you succeed at calculus, and what's left is arithmetic, leave it.
Awesome.
Just leave it like this. Green box, okay, full credit.
This is the thing it's supposed to.
Yeah.
Bring a green pen.
Green pen, that's fine. Green box. But the point of the matter is, I'm not interested in checking whether or not you can do arithmetic. If you check whether or not I can do arithmetic, you'll find I cannot. This is very clear. This is very clear. So there's no need to go down this path. Okay. Right. I mean, there's the actual anecdote that my wife, who's also a mathematician, went out with a bunch of her mathematician colleagues and professors and whatnot. And there was one spouse who was an artist. Guess who did the bill? Not mathematicians. Mathematicians got all tangled up in the details, and just the artist was like, here, let me do it. Right. So the question, though, is how good of an estimate is this? Is this an overestimate or an underestimate? Is 4.15 too big or too small? You think it's perfectly fine. Well, it's perfectly fine as what it is in terms of is the linearization, or is the value given by the linearization. But how can you check? Well, here's how you check. What's that? How do you tell? How do you tell? How do you do that? Let's check. And it's actually pretty easy to check. See, here's our function. Well, actually, I don't even know what our function looks like, right? Remember, we don't even know what this thing looks like. This is what it looks like. All right, so here's our function. This is g prime. Is this thing? I'm gonna label my axes for you. X is square root of x plus 5. Okay, so there it is. And wait, that's totally not what this looks like. That's totally not what this looks like. I don't even know what I'm thinking. Okay. Okay, what does this thing look like? Well, let's see here. As x goes to infinity, it looks like x, and when x gets, okay, it looks like this. It looks like this. And it actually has a slant asymptote. The slant asymptote here is, this one is y equals x, and it's got another slant asymptote, and this one here is y is equal to x. Okay, that's what it is. Right. So that's what the derivative looks like. Now, if we are evaluating this thing at 2, here. So what happens? Where is this 1.95 a little bigger or a little smaller? Yeah.
Can't we use the Newton-Raphson?
Oh, Newton's method. Underestimate, definitely overkill.
Oh.
It's definitely overkill. And furthermore, I'm not even sure how you use it. I'm not even sure how you use it in this particular case, although it's in that same family of ideas. We can do a problem with the Newton-Raphson method if you like. What's that? We should do that. Okay. Okay. All right. So, but coming back to the question at hand, is this an over or underestimate? So this is the value we know. This is A. The value we're trying to estimate is a little less. X. So let's see here. But how are we doing that estimation? Well, we're doing that estimation in the following way. So that's a graph of G prime. Let me try to sketch what's going on with G. So what's G of 2? We know what that is. What's G of 2?
-4.
-4, right. So -4. So G of 2 is here. So our linearization is going to be a line. This is our linearization. Now we're interested in evaluating it a little less. So that's x equals 2. There is 1.95, and you can see that it is, oh yeah, it's gone down a little bit, and indeed down a little bit. Now the question is, did it go down too much, or did it go down not quite enough? Well, if you look at it, what's the derivative doing? What's the slope of g doing as you come this direction? Is it increasing or is it decreasing? It's decreasing, right. So the slope here is becoming less sloping. So the function is becoming less sloping. Still has, at 0, it's still a slope of 5, but it's becoming less sloping. So if I draw g in red, it's here, it's tangent to the curve, but it's becoming less sloping. So whatever g is, this is y is equal to g of x in red there, it's becoming less sloping. So now you can see right away, here's our estimate. Our estimate in blue and the true value in red the true value is just a hair bigger. So this is an underestimate because it's gone down below a little bit. The way you were able to see that is by checking the signs of the derivatives and seeing how they react. Okay. So, yeah, so right, if you wanted to evaluate this at a different point, say at 2.05, here's what you change. You change this number and that number. Yep. And in that case, what's happening? Well, in that case, g is becoming more slopey. My graph isn't quite right here. Graph should look like this. In that case, then you'd end up with something that's a little bit of an overestimate for your answer. All right. Any further questions on this, or should we move to Newton-Raphson? Newton-Raphson. All right, excellent. Newton-Raphson is great stuff. Sufficiently great stuff that we teach a great course in this sort of thing as well. Or more accurately, I teach a great course, I hope. 1 year hence, so next fall, in what is called numerical analysis. We also do some programming too, which is pretty cool. All right, so Newton-Raphson, where instead of finding approximations to functions, what Newton-Raphson does for you is it solves equations. Well, let's see here. Let's get a section number. Newton-Raphson is where in the whole scheme of things? It is 4.8, I think. Yep, it is 4.8. And Newton-Raphson is all about solving equations. And it does so approximately. And not only does it solve equations approximately pretty well most of the time, it solves them pretty fast most of the time, which is why it's a popular way to solve equations. So the idea is, given f, find the x. Okay, so given f, find x. And the way it works it's an algorithm, which means it's actually a prescribed set of instructions. Tells you where to begin, what to do at each stage. And, well, I didn't really tell you when to stop. There are various ways that you can determine when to stop, but how it works is this. We start off with an x0. this is a guess. And it comes from coming as input. So either you make the guess about what that value of x should be, or maybe on an exam, I give it to you. Okay, and then you make a sequence. Of x values, and the rule for computing every element in your sequence is it's based off of modifying the previous one in a particular way. And there's a formula for this. What's that formula? Does anyone know it off the top of their head? It involves f of the previous, and one of these two guys needs a prime on it. Which one needs the prime? Of course, the way written here is xn minus 1. So which one is it that needs the prime? The bottom one. Or the top one? Which one is it?
I thought it was.
It's
Some think it's the bottom.
The bottom one has the
The bottom one has the prime. Okay. Executive decision? Well, I mean, we can certainly go into the book and make sure this formula is right. That's certainly a good way to do this. But a better way to do this is to derive it, of course, if you don't want to waste time. Yeah, the book agrees with you at the bottom. This is actually on page 339. Previously, I derived this from the linearization formula, which is why this topic came up in discussion just a few minutes ago from discussing linearizations. So once we got the linearization, Newton-Raphson Method is a pretty natural thing to try to do to solve equations. That's probably how Newton-Raphson discovered it, if I had to guess. Okay, so this is the formula, and it describes a procedure. So what you do is you can expand this. The idea is you got a sequence, x0. The next one is x0 minus f of x0 divided by f of x0. The next one, well, that we give this a name. We call this x1. The next one then is based off of the previous one. And based off the previous one, oh, right, I give this one a name, and then give this one a name, etc. And at some point, at least doing this by hand becomes rather boring. And at some point, you end up, yeah.
Just for the exam, are you going to make us go to x1 or to x2?
I don't know. It depends on how obnoxious the calculation is. I mean, if you've gone down to like x5 or 6, you would probably quip as the inventor of the computer in the 1800s, quipped, I wish that this calculation were conducted using steam. Because in fact, he was looking to build a computer, and all he knew about at that point was mechanical stuff. And so he was looking to build a steam-powered computer. He succeeded to an extent. In fact, to the point that his designs were later resurrected in the 1980s. Now that we have better manufacturing technology, it was actually built in years. He ran out of money in the 1850s, ran into trouble with grant proposals and related. Got very angry at the British scientific establishment. Interesting chapter in history. Anyway, if you're looking for something interesting to read, the autobiography of Charles Babbage is very, very interesting. Anyway, right, so let's do an example of this. Let's compute something. Let's solve some equation. So for instance, let's take a look at number 20 in 4.8. So 4.8, number 20 says, solve this equation. Solve this equation. Now, of course, solving this equation is like kind of hard. Because if you put in, you know, if you look at it, you say, well, all right, what is it? Well, I've got a cubic on one hand, I've got a hyperbola on the other side. I can certainly have to put it, though, if I'm going to use Newton's method, I can put it in this form, though, pretty easily, right? How do I put it in this form? Just shove everything over to the other side, right? In fact, it would be even kind of convenient for the purposes of computing derivatives to make it into a polynomial. So certainly you could write 0 equal to plus x cubed minus 1 over x. Certainly could do that. That certainly works. Another option is to get rid of that fraction. And solve that equation. Oops, minus. Solve this equation instead. It's worth noting from a mathematical perspective, as in for the purpose of actually solving this equation, these two, of course, will give you basically the same answers, modulo any times when this thing is like divide by 0, but of course that's not going to work out anyway. So you may end up with a spurious extra root here, an extra solution. But barring that, they're basically the same thing. However, Newton's method might give you slightly different answers depending on which you run. I don't offhand know which way works better, but I do know which one is easier to compute the derivative of. Which one? Option 2, yeah. The bottom one is much easier to compute the derivative of. So if you don't have any other insight into the problem, computing the derivatives is easier here. We might as well do this one. Now there's one little hiccup. We need a guess to start this off. So we need to guess what the solution might be. So we'll use the second. Just because x equaling x minus 1 has an easy derivative. Okay, so that that's so easy you can just write it down. Okay, but we need a guess. How am I going to come up with a guess? Okay, so you can just really just guess. Yeah, sure. Yeah, okay. That may or may not work. I have typically bad luck when making such guesses. Maybe you have better luck. There are other ways. I mean, if I put in 3 here, what do I get? I get 1/3 is supposed to be equal to 1 plus 3 cubed. That's 28. That's a pretty bad guess. Sorry. 1/3 is definitely not equal to 28. It's like way not equal to 28. Yeah, 1 is probably a better guess. You know, x equals 1 is a better guess because then you have 1 is equal to 2. It's not quite so bad. Still not right. 1 is definitely not equal to 2. Agree. But it's not quite bad. 0. 0 is definitely a singularly bad guess because you have infinity equals 1. X equals 0. Like 1 plus. That's not so good either. That's just what's that? 1/2. So then I have 2 is equal to 1 plus half cubed, so that's 1/8. Okay, sort of the opposite problem. So, well, but what are we doing here? We're actually doing something systematic, although it seems comical. What we're doing is we're bounding our guess. We found that let me write this down. So x naught chosen to be 3 1/3 versus 28. X naught equals 1. We found that was 1 versus 2. X naught equals 1/2. That's 2 versus 1 plus an 8. See, who's bigger here? This side is bigger, this side is bigger. Smaller, this side is smaller, this side is smaller. So, probably the right answer. Well, actually, never mind, probably. Theorem, the right answer is somewhere between there. So the mean value theorem, or the intermediate value theorem, depending on how you're counting on this, says that the true answer is between 1/2 and 1. So whatever this thing is going to try to converge to, it's got to be somewhere between these two values. Why do I know that this is going to happen? Because this function is continuous. And it's continuous, and if you look at it, it's sort of switched which is which, which is bigger. So if I look at it as this function here, this function is continuous on this interval, and it has switched sign. Well, this function is continuous on the interval, and it too has switched sign, and so therefore the 0 has to be somewhere in between. So a good guess is probably either one of these, and just an important check then is to say which one is, where is it going? If you pick this one and it starts getting smaller and smaller, then you know you've not in a good situation. If you pick this one and it gets bigger and bigger, similarly, not in a good situation. You pick some value sort of in between. Okay. Now, I'd like to probably avoid as much numerical nonsense as I can, since I'm doing this at the board as opposed to on a computer. If I was doing this on a computer, I'd probably I'd probably, just for amusement, try something like 3 and see if it worked after trying the other one. But I'm not at a computer, so I'm going to pick 1, just because we know what's supposed to happen. Okay, so then we run our algorithm. So x1 is x0 minus f of x0 divided by f prime of x0. We've got all the pieces in order. We know what x0 is, we know what f is, we know what f prime is. So let me substitute those pieces in. So this is 1 plus 1 minus 1 divided by 1 plus okay, and let's see, this is 1 minus, what's the numerator here?
No, 1.
Yeah, the numerator is 1, not 2. And the numerator down here, denominator rather, 5. So it's 1 minus a fifth. Is that going in the right direction? Yeah, it's going, x0 is 1. We said it's got to be between 1 and 1/2. This is between 1 and 1/2. It's actually kind of nicely between 1 and 1/2. 1 minus a fifth rather is in fact 4/5. Okay, well you could take this and pop it in again and keep turning the crank until you got as much accuracy as you like. That's enough accuracy for okay. On an exam, just to keep things bounded, I will probably tell you how much accuracy or how many steps I'm interested in.
So you just say, like, you should
Go to x2 or x3 or x15.
Are you going to give us a guess, or will you make us do the
I can see it both 2 different ways. If I'm going to have you guess, I might have you guess from a graph, just so that everyone gives more or less consistent answers. Okay? All right. So tomorrow is going to be another review session, much the same theme as today. So bring your questions, any at all. And again, they will be posted to the internet. So, or at least, hopefully they will be posted to the internet. Assuming you're hearing this right now, It has been successfully posted. All right, perfect.